No program without that.
It's nice to see you all again here.
You too.
For our third presentation
That's great.
about astronomy. If the fourth one is now okay, yeah?
Wow, I missed.
Astronomy. If you are here for astrology, then you are wrong. It has nothing to do. Some people told me astronomy is the real one, and the astrology is the not so real one.
Oh, that's
Wishful
But
thinking.
yeah. And I would like to introduce Phyllis Pitluga.
yes.
Did I pronounce it correctly?
You did.
And she will maybe say something very interesting. I maybe tell this about you. She would like to become an astronaut.
Yes.
And at those times they say, nel pastel, no, because women cannot do this.
Wow.
And this reminds me very close to this wonderful movie, Hidden Numbers?
Figures.
Yeah, hidden
Hidden Figures.
Figures.
That was also something with a black woman. They didn't want most of them in the NASA. So, but Phyllis, it's your
So,
clicker.
thank you for joining me today. And the story of my life I can kind of quickly summarize here with this particular picture. And that is when I was a schoolgirl, my favorite subject in school was science. I always loved it, and I loved doing experiments and blah, blah, blah. And then I decided in those days that my career would be a teacher, because then you were either a secretary or a librarian or a nurse or a teacher. That's what the choices were for careers. Otherwise, you were a homemaker. And I said, you know what? I think it'd be much more interesting to go out and teach science. So that's how I started out. And in fact, as I began university, Sputnik went across the sky. And as it went across the sky from south to north, and I looked up at that from my dormitory balcony, and I said, you know, that's going to change everything. Well, it did. And so as I got involved more in teaching and space and all of that, and I got my own telescope, and I'd use that at night with students and so on, I got fascinated with astronomy. And so I began to swerve more into that. And I did apply to be an astronaut. I did get a letter of rejection. I threw it away. I should have kept it as a sign of the times. And then at one point I got inspired to move to Cape Canaveral, Florida, just to be a part of the space age, even though I couldn't be an astronaut. And I did move there, and I totally enjoyed that. And while I was there, I got an announcement of a summer course being taught at a university where the National Endowment of whatever, NEA, was giving money to school districts to build planetariums because they wanted to have the students catch up with the Soviet Union, which was leading at that point in the space age. And so I said, wow, that sounds interesting to me. So I applied for this summer institute and was accepted. And from that, I began a career in planetarium astronomy afterwards, and ended up at Adler Planetarium in Chicago for 30 years. Yeah, and that's where I did my main, as an astronomer at the planetarium, we gave, in the early days, live sky shows. We would determine as a team, what different themes should be. And so, over time then, we did more and more with exhibits and telescopes and so on and so forth. So that's sort of the background that I have for this presentation today. So here I am at Los Labradores all these years later, and let us begin. So,
We are taping. Be careful.
Okay, you know, our practice runs were in darker elements. I'm having a hard time seeing those pictures, but I do know what they are. And so I'm starting out with the solar system, the planets of our solar system. And, you know, we have along the top the pictures of off to the far, far left would be Mercury, Venus, Earth, and Mars, the four small planets. And then Jupiter and Saturn, the giant planets, and Uranus and Neptune, also giant planets. And of course, when we were all going to school, we learned about Pluto, didn't we? And so that comes into the story a little bit later. So there's also a scale along the bottom that shows that the small planets are closest to the sun, and the giant planets are spread out coming across here. And interestingly enough, this week, planets are going to be visible in our night sky, and with Mercury and Saturn in kind of the dusk glow after sunset. And then as it gets darker, then being able to see the others of Venus out there. And then with the telescope, you could see Neptune and Uranus, but then Jupiter, bright Jupiter, and then Mars. They actually are all strung across the sky, and the moon doesn't become an issue until a little later in the week, the end of the week. So just for the fun of it, I'm going to share with you how we in the astronomy world learned the order of the planets, and that was, it was Mary's violet eyes made John stay up nights panting. And so you did.
Just take me. We are taping you now.
So at any rate, again, this is just for the fun of it. With Mary's violet eyes, Mercury, Venus, Earth, made John's, so MJ, Mars, Jupiter, and then Saturn stay up nights and then panting with Pluto. So that was, but you couldn't do that in public schools and grammar school or anything like that. That would not be okay, but that's how, you know, the college-age students learned them and all that. And so you had to do, my very educated mother just served us 9 pizzas. So that's what school kids learned. So more fun to be an adult, I think, in those days. So that's just was for the fun of it. Now, I'm just going to highlight a few of the planets. I'm not going to go through each and every one of them, but this is the planet Venus that is our next door neighbor, closest to the sun, same size as the sun. No, same size as Earth, excuse me, erase that. Same size as Earth, and yet very, very different. It's a planet that had some early impact that flipped it over so that it spins backwards, whereas all of the planets do go around the sun counterclockwise, but they also spin in that direction. But here's Venus flipped over, still going counterclockwise around, but flipped over, and it has a very thick atmosphere that would make it, it's 100 times more thick than the Earth atmosphere, and it just is, you know, just not a good place to go, that's for sure. So there's your next door neighbor planet, and then the only surface picture that exists is this one that was taken by a Russian satellite landing on Venus in the early days. No one has bothered going back because it ain't worth it. All right, so now we come to planet Earth. We know that one. And Earth is 70%, the surface is water, 30% land. And it is dynamic in that the planets, the continents are in motion by what's called plate tectonics, and of course the core of Earth is hot and gives us a magnetic field and so on and so forth. And So Earth is, we know it as home. And then our neighboring moon, we have, and I think this is the one that, this would be the side of the moon. Let me just make sure from my notes, because since I can't see that, let me just make sure which one came first. Okay, with the moon, again, everything as things formed were liquidy and solidified and so forth, and even the moon had a liquidy world. And as the moon orbited around the Earth, one side would face the Earth, the other side always turned away. And the side facing Earth drew that liquid magma more toward the Earth-facing side, so that when a meteoroid would crash in or something, you'd start to get these black lava seas on this side of the moon we see. So that's our side of the moon. And then the other side, because that liquid was moved the other way, doesn't have those dark lunar seas. Of course, we didn't know that until we got in the space age and said, oh, look at that now, you know. And then if we look at, in this case, the South Pole, and this would be true of the North Pole, there are cratered areas that are in perpetual darkness because it's the poles, and they're in continuous darkness. And so ice has formed there, and now there's an interest, if we were to go back to the moon and, you know, live on the moon or anything like that, hey, why not go near the poles where you can get some water? You don't have to carry a jug of water with you into space. And so that's what this picture is showing. And then this is an experiment that was run by the YouTube spacecraft, taking some plants up to the surface of the moon and seeing, you know, could you maybe as an astronaut there grow your own garden? You wouldn't have to, you know, take food along. Well, it turns out, because the moon has 2 weeks of day and then 2 weeks of night on any one spot on it, that the plants only lived the 2 weeks of daylight. Once it turned to night, it was eternally cold there. The plants didn't make it, and so now we know we can take a little bit of our own water, but we can't take our own plants and grow them there and expect to have a feast. Okay, so excuse me for having a look. I can't see the pictures very well here. Okay, so this must be Saturn with its rings, is it? It doesn't look like it. I have to get up and look. Sorry. Oh, okay. So no, this is Mars, and Mars is a planet that is very different than Earth. First of all, it's about half the size of Earth, farther from the sun. But it has a very, very thin to practically no atmosphere whatsoever, so you'd have to take your own air supply along if you go there. And when you are on Mars, it is not a world at all that seems to me to be habitable. And so but most of our attention in the space age of the different countries has been to go to Mars and test Mars and look at Mars. And it does have an interesting surface in that it has an Olympus Mons there, a mountain that is a very tall mountain, 3 times the height of Everest, and which is impressive. And so some of the explorations have taken us to the surface of the moon And the Curiosity rover was there, and was still there, and doing some surveying for about a 9-year period of time. And during that time, it climbed its Mount Everest, and yeah, so this kind of shows the cratered area there. And there has been some water detected on Mars, subsurface water, so that was of interest to go and test and see. There was a helicopter there that flew for a while, so that was interesting. So that's kind of what's happened with the exploration of Mars. And then now we come to Saturn. Of the outer planets, Jupiter, Saturn, Uranus, and Neptune are all huge, what we call gas giant planets, but they are, they're just all huge balls of gas and that are cold. And Saturn is the most interesting because it does have a visible ring system around it. The other planets, Uranus, Neptune, and Jupiter, have rings, but they're skinny rings in their edge on, and we don't really see them. They don't show up. But Saturn is tipped about the same amount as Earth, and lo and behold, we can see those rings, and they're impressive to look at. And then it has something like, I think it's 6 moons that we can see in a, just casually in a telescope, and then in a big telescope or space age exploration, about 60 moons going around it. And that's characteristic of those outer planets too. They're big gas giants with skinny rings and with lots of moons. So you start with the inner solar system, and you've got these small rocky worlds, and then you get to the gas giant worlds, and that's sort of the planetary world. And now we go, in this one, I get my pointer out for this. Let's see if this pointer works for you or not. Right in the center is where the sun is, and then just immediately around it is where, Mercury, Venus, Earth, and Mars are. And then you've got Jupiter, Saturn, Uranus, and Neptune kind of forming a little ring around that. And then we've got what's called the trans-Neptunian world is out here. Hello. And so what I wanted to do was spend some time on the outer solar system. So the trans-Neptunian world, as telescopes and space probes were spending more and more time out there, began to learn of a lot of them. Again, these are planets, well, planetoids of the sun, but they don't. In 2006, the International Union of Astronomers said, no, Pluto is not a planet, nor are any of these. They are small. They don't sculpt out their own world, their own realm of orbiting like the other inner planets do. And so this just gives you a context of why Pluto doesn't get counted anymore. So we dropped it out as an official planet, and poor Clyde Tombaugh, who discovered Pluto, was still alive when that happened, and he heard about it. His planet got demoted. Okay, so now then, this is symbolic of an area two areas. This is symbolic of 2 areas. Between Mars and Jupiter, so you've got Mercury, Venus, Earth, Mars, and then between Mars and Jupiter, in the beginning of the gas giant planets, we've got this world of asteroids. And I had meant to put in an asteroid photo, and I didn't get it in. So you're just going to have to picture a big, lumpy world with lots of little craters on it and things like that. Again, not a place you want to go to. And so those asteroid worlds orbit around that area between Mars and Jupiter. But every now and then one gets gravitationally pulled off course and drawn in to the inner solar system. And so you've probably heard about this asteroid that could be hitting Earth in 2032. Okay, so this asteroid, two things about to know about it are, as more and more observations have gone on with it, and right now it's actually moved beyond our field of view, and then will come back into the field of view, blah, blah, blah. But right now, the odds have gone down to 0.3% chance of it hitting Earth, where it was starting out as, oh, it's going to hit the Earth on December 22nd, And so, but then I keep thinking, well, now, wait a minute. Planet Earth is covered 70% by water, so what's the likelihood of it landing in Chicago or in San Miguel or wherever? You know, it's probably, I mean, we do get meteorites. In fact, I have a collection of meteorites that have, you know, from stuff that has landed from space. And it does happen, but big ones is the issue here. So, at any rate, not to worry is what I'm saying the current reading is on this particular one. So then the other part of this image is of a comet. And this is Halley's Comet, which probably some of you saw back in 1986 was when Halley's Comet came by. And how many saw Halley's Comet? Anybody? Okay, good, yeah. It was a thing to go out and watch and view, so we did. And so there's a realm of comets that orbit beyond Neptune, and then there's also a bigger shell of comets farther out. So if we look at a cross-section of the whole solar system, we go from the sun, which I'm coming to next, the star of the solar system, and then we have the rocky planets and the gas giant planets, and then we have, and in there the asteroid belt, and then we have a realm of comets around, you know, in a circle, and then some that get pulled in. So the solar system is just a big bubble, basically, in that sense. So, now, changing from planets to stars, and this is a photograph of our sun, and kind of a boring photograph of it. This is during a total eclipse of the sun, where you can see the outer atmosphere of the sun and its dynamic world, and then a composite astronomical picture that shows the magnetic field of the sun on there that gets twisted as the sun spins and all of the dynamics take place. And so on an 11-year cycle, more or less, the sun is quite active, and then at other times it's not so active in terms of spraying stuff out into space. Coronal mass ejections, look out. And so currently we're in that high period of solar activity, and it's the kind of thing where you get to see the northern lights, or the aurora borealis, northern lights, southern lights, and then, but at this latitude, I have to say, 20 degrees north of the equator, we don't see it down here. But that's why you get invitations to take a trip and see the northern lights, and if you're going to do that, this is the time to do it, because it's the time to, of the activity of the sun. And so, that's the good part of it. And then you get radio blackouts and things like that. There's some negatives to the activity of the sun as well. So that's that. And so this shows our magnetic field that protects Earth from a lot of the radiation and activity of the sun, which is good. So there's the sun, and then this is not to scale clearly, but Earth's magnetic field does protect us from a lot of the dangers of the sun. Okay, so now the sun being a star, that leads me to this chapter of the talk. And how am I doing time-wise, okay?
Good, yeah.
Good? Okay. Yay. Stars, when they are born, and that means they are clouds of gas and dust that as they swirl around, it's like an ice skater drawing in arms, and as the gas comes in, it goes faster and faster and faster, and the star gets hotter and hotter in the center and starts to really cook and be a star and go through nuclear reactions, and that's building up the elements on the periodic table of elements. If you took chemistry, oh yeah, I remember that. Well, that stuff is made in stars, and stars, can be big clouds, little clouds, and this is what's called the main sequence, where you have little red stars, medium-sized sun stars, and then blue giant stars out here. But this whole thing is the main sequence of stars. And then as stars evolve, they can become red giant stars and supergiants or white dwarfs. So the main sequence of stars is like this, and that gives you the brightness, temperature, their thing here. And another, once upon a time, I'm seeing the letters down here for these stars come in different classifications. Our star is a G star. Well, where did those come from? What's that all about? When the star classification started, there was a sensible order, ha ha ha. But then when we learned more about the stars, it was not the right order anymore. So now you've got a screwy alphabet at the bottom there. And so once again, astronomers enjoying humor, the way we remember that is, oh, be a fine girl, kiss me now. So let's look at some evolved stars. So this is our closest, brightest star, and its name is Sirius, and so this is that star, and then, yeah, you're seeing a little star here, are you?
Yeah.
Okay, good. I can't see it, but I think it's okay. And that is, it's a white dwarf companion star, so it's a double star system, and a white dwarf star is a star that didn't make it, and then the other one is doing just fine, thank you, right now. So then another star example, one of my favorites, is Betelgeuse in the shoulder of Orion, and it's a red star. And about 2 years ago, there was a concern because it was fluctuating in brightness in ways that stars don't normally do. And people were saying, oh my God, it's going to explode. And then it didn't. Well, but it still could. And it's 520 light years away, which means that maybe 519 years ago it exploded, and that image of an exploded star is about to hit us in the face here. So watch out. If you hear that Betelgeuse has exploded, and that's up in the shoulder of the constellation of Orion, for those of you that happen to know your constellations, and it's a constellation that is nicely placed high overhead in our sky right now, and because Betelgeuse is a red star, and red star, and then it has a belt of 3 stars, and then hanging from its belt is a nebula that I'm going to show you a picture of. And at any rate, it's a nice part of the sky and some nice imagery. And now, let's see. Okay, so this is what's called the Ring Nebula. And this is the future of our star, the size of our star. At some point when it no longer can fuse elements together and create heat, it will kind of die in the center to a white dwarf star like you just saw there. And its atmosphere will go floating away. So if we're on Earth 3 billion years from now, when that happens, we'll see, the atmosphere of the sun come wafting across, and we'll be somewhere down in, very near to the center of it. So it's an interesting dynamic part of what we see out in space, but part of the story of a star and what goes on. And let's see what I have next here. Okay, so then the most dramatic part of a star's life is the ones that explode when they die. They no longer are creating the heat and temperature to create heavier elements and all of that, and they explode as supernovae. And this is a Crab Nebula that exploded, was visible to us in 1054 AD, well, not to us, but to our ancestors. And in 1054 AD was recorded. Let's see, however far away it was, it had taken time for that image to reach Earth. And so this is how the galaxy that we're about ready to move into is getting enriched with elements from exploded stars, casting out all of this enriched stuff. So that's the Crab Nebula, and leads us to, and this is a star that it could be exploding, and I'd have to check my notes because I forget how many years away it could be. Let's see, put that here. Next page. Okay, yes, so this is the Eta Carina, ready to burst, and it's 10 times the mass of the sun, so yes, that'll be a super duper, so who knows when, but at any rate, that's the Eta Carina, ready to burst. And so now, having taken you through, there we go. Having taken you through stars with planets around them and how their lives go and then how they die, let's get to star birth. How about that? Because that goes on today and in our own galaxy and in other galaxies. And so this is a pretty picture of an area of the sky where star birth is going on, and this is the Orion Nebula I was mentioning that is dropped down from the belt of Orion, a pretty thing to look at in the telescope. And I have a couple of images here, and not able to see as well as you can. But if I lean forward, that helps. It's the dark areas where the stars are being born. The bright areas, no, but where we can record star birth is in the dark areas. And so a lot of time with telescopes is spent looking at the star birth regions. And I have a couple of examples of that. Again, look at the dark areas, and then you can see the bright stars and the clouds that are already lit up. And then this is a neat picture of a star that has just ignited and is forming a solar system. It's forming a solar system, and that gives you an idea of what happened once upon a time here. So, and you get the idea of close in and then farther out where comets are and all of that. So you have the solar system formation allowing you to have the dynamics that we saw in our own solar system. Okay. And then I'm sure many of you looked at the Pleiades up at nighttime, and this is the Pleiades. And you can, I put this in because it's a pretty picture, and you can see, you know, the young gas around it still and so on. And anyway, so that's, star birth is an ongoing event in our galaxy and throughout the galaxies of our universe. Now, this is an image that was taken by a spacecraft that spent about 8 or 9 years out looking for planets around other stars. It's not easy to see planets around other stars from where you are here on Earth because you got a blurry atmosphere and blah, blah, blah. And in that time, these are some examples, and what was found was that planets outnumber stars because, now look at our own star, the sun, one sun and a bunch of planets, right, in all different sizes. And that's also the case out in space, is that finding other stars that had planets, and you know, many of them were of a similar ilk to the United States, so, oh, maybe there's life elsewhere in the universe, but we've not found it yet. We don't have evidence for it yet. They're still unknown. But the possibilities are there. And now back to our Orion Nebula to move on into galaxies at this point. So what you get the exploding stars that are enriching space and enriching what goes on. And since I can't see the picture, I have to look at my notes to see what it's supposed to be showing. Okay, so this is a star out there, and it's let's see, this is a neutron star that's a pulsar that pulses. But it's the idea that stars are parts of galaxies, and then when we move on, we begin to see the bigger picture. And in the case of our own galaxy, wait a minute, picture's missing there. I'm going to go back one and see if, oh, I told you the wrong story, but it's this, okay, starting over with this one. This is what's called a globular star cluster. And they are globes of stars that are around our Milky Way galaxy. They were discovered in 1950 by a woman astronomer, Vera Rubin, who now has a telescope named after her that's going to begin searching for what she discovered in 1950 is that there's something that was holding these globular star clusters to the Milky Way, and it became named dark matter. You've probably heard about dark matter, and that continues to be a big mystery, I will add. But in looking at these globular star clusters, she says something is holding them on, and as they do, they are then circling around. So they're part of a halo to the Milky Way galaxy. And these are two views. An edge-on view, if we were out in space looking at the Milky Way, we would see it would have a bulgy center and then flattened spirals that swirl out around it. And then this is a face-on view, so there's the center, and then this is looking down on our Milky Way galaxy. And where we live is we live about 2/3 of the way out, and not in one of the spiral arms, but on what's called the Orion Arm. We even know where we live in our galaxy of our island of stars, and that's due to lots of research. And so this is a composite made-up picture of our Milky Way galaxy with the dark matter around it that's holding on the halo. And of course, this is what we don't know what that matter is one of the big mysteries right now that's going on, is what is the dark matter? And then if we look at our galaxy at the very center, it's what we in astronomy call a Sagittarius A star, because it was known but not known what it was. It's now known to be a super black hole. And the center of galaxies do tend to have super black holes. And I'm emphasizing the word super because now I want to take time and say, as stars collapse at the ends of their lives, you know, you get your white dwarf star, you might get a neutron star, so on, and then you can get star-sized black holes. But these are super black holes that are gigantic, and so we now know that about Sagittarius A. So there are two types of black holes. Little ones that are, you know, collapsed stars, and big ones that are at the centers of galaxies. And then what's interesting about those super black holes is that as gas gets swirled in to the black hole, and that's what makes it black, it's staying black, but there can be jets of gas that squirt out of the poles, and those were what were first identified as quasars. And quasars are the spurts that are coming out of the super black holes at the center of galaxies. Did you get all that? And so, now this is our neighbor galaxy, the Andromeda Galaxy. A beautiful thing to view in a telescope. And again, if this were our galaxy, we'd be about 2/3 of the way out from the center. And then this one shows that it has a small companion galaxy. Well, the Milky Way does too. We have the small and large Magellanic Clouds that are our neighbor galaxies, and are more visible in the southern hemisphere than here, but nonetheless, they are part of the Milky Way galaxy. So we have our companion. Oh, and now I'm going to show you a bizarre composite photograph that it is, well, it's not a photograph, it's a made up, but the way we view our Milky Way in the sky is as sort of a line of stars. You know, if you've gone out, especially in the summertime, you can see the beautiful Milky Way stretching across the sky. Well, it turns out that Andromeda Galaxy and the Milky Way galaxy are getting closer and closer and closer together. And the thought was, oh my God, we're going to collide with that huge neighbor. But the latest news that I've been reading, and today I'm presenting the latest I know, so this is the best we're doing, is that that the Andromeda Galaxy is coming at an angle, and maybe it's not to worry in the future, long future, not our future. So that is part of the history of the galaxies in the Milky Way galaxy. And let's see. And this is a diagram that shows what we call our local group, and I think, yeah, there's the Milky Way there. And because it's focused on where we are, and that doesn't mean we're the center of the local group. For us, it's the local group around us, but each star, or each galaxy could have its own local group. This is our diagram, and you see Andromeda Galaxy here being drawn closer and closer to our Milky Way galaxy, and we will see, we will see. It may be a miss, anything. The point is that things are dynamic out there, even in the bigger picture of galaxies and galaxies making up the universe. And now, this is a picture that was sent to me from Dieter the other day, and it's a scale picture that shows the sun and then the size of the Earth compared to the sun.
Wow.
Yeah, wow. And that means if you happen to see a sunspot sometime, the Earth would fit in that sunspot. That's how I always think of sunspots, as they're Earth-sized blobs on the sun. And then if you take the whole sun and compare it to this other star, there's a big difference here, obviously. And then I'm thinking, since I didn't do the research on this one, that this must be a super black hole in the center of a galaxy, and then, you know, the biggest star compared to the black hole center, and there's a big difference there too. So then we get to our final picture, and this one is a timeline of the universe, and so, and what we know and how we know it. So the Big Bang would have occurred here, and the time is going across here of 13.7 billion years.
Wow.
And this particular spacecraft was mapping the earliest light, and I'm having trouble seeing, but I think it's this band right in here. And it's the microwave background radiation. The first radiation that we could map was microwave, and it was done by that spacecraft in 2013, as I recall. And so then after that, there was a dark period, and then we began to see the first stars. And from the time of the first stars, the universe has been expanding outward. And so all of this activity that I've been talking about, star birth in the Milky Way galaxy with planets around it and blah, 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 all of that has taken place activity-wise over the last 13.7 billion years until we get to today, where we're out here looking at our universe. And the big surprise, the big surprise is the universe is accelerating. See how this suddenly dips up in here? So before, it seemed to be kind of a continuous expansion. But now it seems like there's something that is inserting extra energy into the universe and causing it to accelerate and things to go farther apart faster. And that's what's called the mysterious dark energy. So I leave you with two mysteries. What's dark matter and what's this dark energy? And that's my story today about the universe. Thank you.